monitoring corresponding to their task to anticipate future possibility that the same phenomena will occur at other volcanoes. Many collaborative activity among government institutions has been conducted, such as dual real-time seismic monitoring between CVGSM and Meteorological, Climatological, and Geophysical Agency, and also Agency on Technology Assessment and Application, which have installed tsunami early warning system around Anak Krakatau volcano island. Therefore, I once again congratulate you on attending this seminar. I hope that from this seminar, we all get new perspectives that are useful for all of us in contributing to better mitigation. Thank you.
Okay, thank you. Thank you very much, Dr. Hendra, and thank you again for the invitation to come and speak today. I really appreciate this opportunity, and thank you everyone for coming to listen to this seminar. And I think I absolutely agree that, as was just highlighted, there are many challenges remaining with understanding the processes that lead to volcanically generated tsunamis, and in obtaining the type of monitoring data and recognizing the signals that might precede these events. And one of those challenges that I want to emphasize in this talk is the diversity of processes that can potentially generate tsunamis at volcanic settings. These are not simple events that all have a common trigger or a common set of processes. So this sort of variety of potential tsunami sources presents a major challenge. And although our ability to forecast volcanic activity has improved very significantly in the past few decades, our ability to forecast the specific style and outcome of an eruption is more difficult. And that is particularly important if we want to understand whether an event is likely to proceed in the style, say, of the Anak Krakatau event in 2018 and become tsunami generating. So there are many uncertainties that remain. And in this talk, I'd like really to give quite a broad overview using a few different case studies of volcanically generated tsunamis. So hopefully give you all an understanding of this topic in a sort of general sense, and some understanding of the current research that we are doing that seeks to improve our knowledge of how these events are generated. So I will share the screen if I can. Let me just try this. I think this should work.
I think before you start the talk, I would like to say hi first to the audience. Please wait for a moment.
Yeah.
Yeah.
That's fine. Thank you. Yeah.
Okay, good afternoon, ladies and gentlemen. First of all, thank you very much for your coming, especially for our invited speaker, Dr. Sebastian Watt, and also for Dr. Hendra Gunawan from GPGSM. We would like to thank for your coming in this guest lecture that organized by Geological Engineering, Faculty of Earth Sciences and Technology, ITB. We really appreciate for your participation. My name is Mirzam from Geological Engineering. I will be your moderator for today. We still remember that on 22nd December, almost 2 years ago, the lateral collapse of Anak Krakatau generated tsunami, which killed more than 400 people and displaced more than 16,000 people. This is the reason why we invite Dr. Sebastian Watt to share his knowledge and to discuss more about Anak Krakatau. Okay, before we start the guest lecture, I would like to inform you that this guest lecture actually is part of our collaboration with many universities in the United Kingdom, including Oxford, and then following by BGS and also University of Birmingham, National Oceanography Center, and etc. The topic of today's session will be volcanology. Today we will discuss about the tsunami hazard at island volcanoes. Let me introduce the invited speaker, Dr. Sebastian Watt. Please wait a moment. Dr. Sebastian Watt, he got Master of Science from University of Cambridge 2006, and then 2010 he got the PhD from University of Oxford, and then 2014 become lecturer in the Earth Sciences of University of Birmingham. I also would like to send my warm greeting from our Dean, Dr. Iwan Melano. Unfortunately, he cannot join because today is our graduation day in ITB. Okay, ladies and gentlemen, before we start the talk, let me to inform you that there will be question and answer at the end of the presentation. To ask the question, the audience may use question and answer feature in the Zoom or write your question in YouTube comment. Following the format, name underscore institution or affiliation underscore question. Due to the limitation of time, we will select only 3 questions and continue to the remaining if the time is adequate. Okay, without further ado, please welcome Dr. Sebastian Watt from University of Birmingham. The time is yours.
Thank you very much, Nizam. Thank you. Right, I will. Let me try this. Will this work? Okay, so I hope you can now see the presentation that I'm sharing. So yes, thank you once again for inviting me to give this seminar today. I'm very pleased to be able to talk on this topic. This is a topic that has been of interest to me, I think, really right back since I was working on my PhD in 2006, actually at a volcano in Chile. And this volcano in Chile in the 1960s had a partial collapse on one of its flanks, and that landslide entered a nearby lake and generated a damaging displacement wave, a form of tsunami within this lake. And this got me interested in this topic. And then subsequent work that I did in Southampton, offshore the island of Montserrat, and then in other locations led me to go into greater depth, into better understanding the volcanic processes that, first of all, lead to edifice instability in general, so the failure of a portion of a volcanic edifice, and in island settings, how those processes can then be tsunami generating and how we can improve our understanding of that process. So there are many people that have contributed to this, and as Mirzam has mentioned, we have this ongoing collaboration working with people at ITB at sites in Indonesia, particularly at Krakatau, and there are many other people that have also contributed to some of the work that I'll be presenting here today. So I'd like to thank all their contributions, which are too many really to list on this opening slide. So I have a picture here of an island in Papua New Guinea. This is in a string of islands called the Bismarck Volcanic Arc, which is north of the main island of New Guinea. And there are several small volcanic islands in this arc. And one of them, which is not a particularly well-known site today, is this volcano here called Ritter Island. And what you can see behind the ship is the remnants of the subaerial edifice at Ritter. So before 1888, this was quite a prominent conical volcanic island, steep-sided, with the flank continuing beneath sea level. And this was quite an active volcanic island as well. It had undergone many eruptions that are recorded in the 17th and 18th centuries. And then in 1888, without any recognized warning, nearly all the subaerial part of the island disappeared in a single catastrophic landslide. And this generated a devastating tsunami that caused damage to distances of around 500 kilometers. We know that from contemporary reports. And that certainly caused very severe damage to coastal settlements on many of these surrounding islands. The precise detail of those impacts are not very well documented, but we do have some information about this event from observations of the size of the wave at various locations around the region. And from previous reports, we can reconstruct to some extent the size of this collapse. So this event at Ritter demonstrates very clearly the potential impact, the potential very damaging impact of volcanic generated tsunamis via a landslide or an edifice collapse mechanism. And was really the best historical example that we had to learn more about this process until 2018, when a broadly comparable event occurred at Anak, Krakatau, which, as I'm sure you're well aware, was better observed and for which we have a wealth of data in which we can better understand the processes that led to this style of volcanic event. But I point out Ritter first because it provides another example from which we can try to learn more about this process. So this is an aerial view of Ritter, and hopefully gives you a clearer impression of the failure of the volcanic structure. So you can see on the left of this image the sort of remnants of the cone, this flank here, and you can get a sense that this was a conical volcanic structure, and you can see the big horseshoe-shaped scar from which most of the edifice failed and was transported into the sea. Now, there are actually drawings from before the event of what Ritter Island looks like, and so we get an impression of the size of the edifice. This had a height of maybe 800 meters or so, was certainly steep-sided, and was typified by Strombolian-style eruptions from the descriptions, and a broadly basaltic volcano. So in many respects comparable to Anak Krakatau, a slightly bigger island, but there are some common processes and styles of behaviour. Now this is some marine mapping data that actually was collected on that ship that you saw in the previous photograph. And the aim of this research was really to start better understanding the process of the Ritter Island collapse in 1888. And we do that by looking at the landslide deposits that it generated. That helps us understand the breakup of the edifice, the movement of that landslide, the volume of the failure by reconstructing from the deposits of the landslide, the primary volcanic volume. And also from the distal stratigraphy of the landslide deposits, which are sandwiched between volcanic deposits. We can also try to start reconstructing the behavior of the volcanic island around this time. So for example, at Ritter, we have found that the collapse was followed by an intense eruption, probably a submarine eruption, that immediately followed the event. And the composition of that magma was actually quite anomalous in the context of previous activity at Ritter. Now, what you can see here in the scar of the Ritter failure, so this is entirely submarine map data here. You can see the cone that has grown inside the failure scar. So Ritter remains an active volcano and is regrowing, but it's still beneath sea level. The base of the failure plain was about 800 meters beneath sea level. So overall, this event at Ritter moved from an edifice that was maybe 800 meters above sea level to one that was perhaps 800 meters below. So about 1.5 kilometers of rock was moved in a single catastrophic event 1.5 kilometers of rock that overlay the active magma system, and as you could appreciate, perhaps has changes in the configuration of that magma system as a result. And all of that mass broke up and was transported into the sea and across the seafloor. And this is a map based on the work we've been doing that I just show briefly to sort of show how we can reconstruct the features of this event. The behavior of these landslides is quite complex as they're placed on the seafloor. What we see in many examples is extensive interaction and erosion with the pre-existing sediment on the seafloor. This means the final deposits can be of much greater volume than the initial failure because of this bulking and interaction with the seafloor. We can see in these mapped boxes that sort of focus on particular areas. We can see evidence of erosion of the seafloor by the flow as it moved over the surface. We see that again in this map here as the mobile flow was forming a pathway over the seafloor. Now, Ritter, quite unusually in some respects, appears to have disintegrated very rapidly and formed a very mobile debris flow that travelled for over 80 kilometres into the surrounding basin. So you can see perhaps on this map that Ritter is a sort of quite a small island in the bottom right corner, and the landslide deposits cover a vast area. These were extremely mobile. Current results from Anak Krakatau suggest quite a different style of landslide failure, in fact, and that the Anak Krakatau failure mass broke up much less and was not dispersed this widely. In terms of the tsunami generating process, that difference may not be of primary importance because the most important stage for generating a tsunami is the initial stage of failure. So just to summarize from Ritter, this landslide had a volume of perhaps up to 4 cubic kilometers, so 2 to 4 cubic kilometers. It dispersed material for around 80 kilometers on the seafloor, and the tsunami was damaging at distances of over 500 kilometers. And there's just a geophysical sub-bottom profile there that shows the type of data we can use to actually reconstruct the volume of this event. So we can image the surface and the base of the deposit, identify evidence for erosion, constrain the total volume, and so on to piece together the event. Now, there are many islands globally where we can identify deposits of this type of process. Now, many of these are very old. These may have occurred thousands or tens of thousands or even hundreds of thousands of years ago. So these are not necessarily very frequent events, but we have evidence around many volcanic islands that they can occur. And we know this more generally around volcanoes from continental settings as well. So the process of sector collapse, of failure of a part of a volcanic structure to generate a landslide deposit, or what sometimes are called debris avalanche deposits, is a ubiquitous process, but these are not frequent events in the lifetime of any particular volcano. So instability of volcanic structures is a general process. Now, what I show on this global map is the sites where we have offshore mapping of volcanic debris avalanche deposits, so island sites. And we can infer that these events would have been tsunami generating. And you can see that the distribution of the events we know of is quite clustered in particular locations. So the Bismarck Arc on the right, where Ritter is located, the Lesser Antilles Island Arc, where Montserrat and many other islands have been studied, and so on. Now, this doesn't mean that those arcs are unusual in being capable of generating these events. I think this is more a factor of areas with high resolution seafloor mapping where these have been studied. So there are many arcs that we haven't studied for this type of process, but it's very likely that comparable deposits occur in those settings as well. So volcanic islands are potentially prone to this type of process, but I emphasize again, this is an infrequent event. And because it's infrequent, we don't have a good understanding necessarily of these hazards. We don't have many examples in the historical record. But I just want to point out this as well to sort of emphasize the importance of improving that understanding. Of all tsunamis, whatever the generating mechanism, volcanic tsunamis are quite a small subset of those events. Maybe 5% or so of all tsunamis have a volcanic source, a volcanic origin. But when we look at volcanic hazards, and if we specifically say look at events that have caused fatalities, so this is just volcanic events in this table here. You can see that volcanic tsunamis are high up on this list. A relatively small number of events, most particularly the Krakatau 1883 eruption, but also a number of other events, have been responsible for very severe impacts. So although you might not sort of initially think of tsunamis being a particularly prominent type of volcanic hazard, they are high up this list in terms of their potential to cause very severe impacts. So these events may not be common, but they have devastating results and are important for us to better understand. Now, all I've mentioned so far really are landslide-generated volcanic tsunamis, but one of the difficulties with understanding volcanically generated tsunamis is that there are in fact a range of mechanisms that can generate water displacement from volcanic processes. So all we really need for this to happen is a volcanic setting that is close enough to a large water body that there can be displacement of that water. And that can be in the form of a flow entering the seawater, so a primary pyroclastic density current, for example. It can be in the form of a landslide failure, which may or may not be related to eruptive activity. So these are not necessarily always linked to eruptions. It may be from a shallow or underwater eruption itself. So there are different mechanisms shown here. And it could even also be from a subsidence type mechanism accompanying caldera collapse. So as we're going to see in the 1883 eruption of Krakatau, there really is still a lot of uncertainty as to the precise mechanism that generated the tsunami. And it's possible that that mechanism is complex and involves a variety of these processes. And just as one more example, very briefly, Unzen in Japan in 1792. Unzen, a highly active volcano in Japan, and in 1792, actually an older part of the volcano of Unzen, so an inactive part of the volcano, failed during an eruption of Unzen, but also triggered immediately by a series of local earthquakes. This older portion of the volcano failed in a volcanic landslide, and that entered a nearby bay and caused a tsunami that inundated the shoreline on the opposite side of the bay. And this remains the worst volcanic disaster in Japan in terms of the total number of fatalities in the event. So a very severe volcanic disaster. But it really highlights again the complexity of these processes. This was a landslide generated tsunami on a volcanic structure, but not necessarily directly linked to the eruption, and not involving sort of fresh material from that eruption. So another event that sort of highlights the challenges with identifying instability and understanding the potential outcome. So just to sort of summarize before we get to look at more detail at Krakatau, the current volcano monitoring techniques can help with forecasting the timing of eruptions. They can identify unrest but it's much harder to forecast how that event will proceed. So the style of the eruption and the size of that eruption. But those later parameters are important for understanding if there's a potential risk for tsunami generation. Tsunamis can be a consequence of different volcanic processes, and these may or may not be eruption related, and the impacts are far-reaching. And because they're infrequent, we have relatively few historical events that we can learn from to improve our understanding of this process. So we'll now go to look at Krakatau, and from a very sort of small data set of volcanically generated tsunamis, particularly large volcanic generated tsunamis, Krakatoa is very unusual because two of those events have occurred at this particular volcano in 1883 and in 2018. And these are quite different events. So there's many contrasts between them. In 1883, as I'm sure many of you are very familiar with, there's a very large magnitude explosive eruption of Krakatoa, a caldera forming eruption that destroyed much of the island at the time. And associated with the culminating phase of that eruption, there was a devastating tsunami that affected all of the straits between Java and Sumatra, but also that wave was measurable over much, much greater distances. After that event in 1927, Anak Krakatau first emerged above sea level and continued to grow until 2018, when that young volcanic structure failed through a lateral collapse through a landslide on one of its flanks, and generated a very damaging tsunami again via that mechanism. So quite different mechanism, and in some respects quite a different volcano. We have a large magnitude eruption of viscous rhyodacite, so silica-rich magma in 1883, and we have a basaltic andesite volcano characterized by strombolian eruptions, so much sort of less intense explosive activity, failing in 2018 via a landslide type mechanism, but at the same volcanic system, these two events occurring, and spaced apart by only 130 years or so. So we'll look first at the 1883 eruption. And this event in 1883 was caused sort of great interest and was a very dramatic event that was known of around the world. So this was shortly after the communications via the telegraph were in place, and so very rapidly news of this event spread, and there was interest in studying the event as well and the impacts of this event. This was a volcanic eruption on an extreme scale, and the direct effects of that, of course, were extremely devastating in the region, but were also observable to very great distances. And as a consequence of that, there was a lot of information and study of the event at the time that provides a record from which we can piece together the process of the eruption itself and the generation of the tsunami. So I just show as an example of that this newspaper cover from 1883, early September, documenting in the UK the outcome of the event and describing what had occurred. And this raised the interest of scientists at the time in terms of the range of phenomena associated with this very large explosive eruption. So this, as an example, is from a painting that was done of the dramatic sunsets that occurred over London in 1883. And it was recognized that these were a consequence of the aerosol that had been injected into the atmosphere by the explosive eruption, and of course these very far-reaching effects. Similarly, the pressure wave from the eruption in 1883 was measurable around the world, as well as the water waves over a very large distance. So this was an eruption on a very, very large scale. And this magnitude of the tsunami was correspondingly extremely large. So this is one of those maps that was, at the time, this is from a study by Verbeek. It's a copy of one of those maps. And it shows the aftermath of the 1883 eruption and picks out the impact of the tsunami from that event. So I just want to highlight two things on this map. Notice that this is quite a big scale, so it's showing Sumatra and much of Western Java, and you can see the scale bar at the base. And two things to point out. So the first of all is the change in the shape of the Krakatau Islands that accompanied this event. So the main island of Krakatau was previously quite a lot larger than the remnant of it is today. The remnant is now called Rakata. But the main island shown by the former outline here on this little map further north, and there were a number of vents, active vents on that island. So 2/3 of that main island disappeared as a consequence of the event through a combination of caldera subsidence and the explosive activity itself, and possibly coupled sort of landslide type events. So dramatic changes in the morphology of the island. And the second thing I want to point out is that even on the scale of this regional map, the inundation of the tsunami can be mapped. So it says here the dotted space shows the coast submerged by the wave. So you can see in Eastern Java that there is inundation to distances of 10 kilometers or more in places by this tsunami. So extremely far-reaching impacts along all of this coastline, and indeed in these bays, to Telok Bitong and in Semangka Bay on Sumatra. The devastation that this wrought on those coastlines was also extreme in its extent. So you can see that very clearly from some of these images here of destruction of masonry buildings, of rail, of sort of iron and steel structures. So you can see this sort of engine here in the top picture. And this wave was capable of transporting very, very large blocks of rock. So this is a coral reef block that's been carried hundreds of meters inland. You can see a man standing next to this for scale. So you get an impression of the sheer capacity and destructive energy of this wave for carrying debris and also for causing destruction. And that's also sort of demonstrated, I think, by this well-known image of a steamship in Telok Bitong that was carried 2.5 kilometers inland and left stranded in this valley, well inland by the wave. And the mooring buoy from this ship is still in Telok Bitong today, as you can see there. So just want to talk briefly about what we know about the 1883 eruption tsunami, and then perhaps to highlight what we perhaps don't know so well and what would be we would ideally aim to better constrain to understand the tsunami generating mechanism. So the 1883 eruption had begun in May, and there had been several months of eruptive activity until the main phase in August. The May eruption itself was quite a large event. The explosions in May were heard over very large distances. This formed pumice rafts in the sea locally. So this was still a significant Plinian-style eruption in May 1883. And activity at Krakatau then sort of continued for several months, possibly at a slightly reduced level of intensity, and then started to build up again in August. And the main phase of the eruption culminated on the 26th and 27th of August in around a 12-hour period. So that's important to understand, that the main phase of the eruption lasted many hours, but the tsunami was only generated at a particular point, or the most damaging tsunami was only generated at one particular point. So it would be oversimplistic to say that all of that 12-hour eruption was generating the tsunami. There was a particular stage, particular process near the end of that eruption that generated the extreme magnitude tsunami. And the origin time of that wave, based on its arrival at various sites, can be put back to around 10 a.m. on the 27th of August. And that ties in very closely to the timing of the largest explosive signal at 9:58, as you can see highlighted here. Now, there were many other large explosions during this 12-hour period. I've highlighted a few of them. This 10 a.m. one stands out as being the strongest. But although it's the strongest, there are other events of similar type, perhaps. But there must have been something distinctive occurring at 10 a.m. To be responsible for generating the wave of the magnitude that was observed. This explosive record, by the way, is obtained from the record in Batavia at the time, from the gasometer, and it's a measure of the air pressure wave signal. So disturbances or fluctuations in air pressure resulting from this explosive activity. And so this is picking up these very sharp fluctuations from the volcanic explosions. So we know that this eruption lasted many hours. We know that it involved many pulses of explosive activity. And we know that tephra fallout was occurring through this period. And there is good evidence of, it's very likely that there were PDCs, pyroclastic density currents, being generated through this period as well. What we also know from reports on the coastline of Java in particular, but also near Teluk Bitong, is that there were smaller but still very damaging tsunamis occurring in the Sunda Straits through this period. So the town of Angers had been very badly damaged at 6 a.m., for example, by a tsunami. So these earlier stages of the eruption were still generating tsunamis, quite likely by pyroclastic density current entering the sea. But the damage of those was sort of restricted to within the Sunda Straits, and although damaging, nothing like on the scale of the main 10 a.m. event. We can look at the aftermath of Krakatoa as well to sort of understand the magnitude of this eruption. So this is from a drawing taken from one of those studies that aimed to reconstruct the event afterwards. And we can see a few important features that sort of emphasize the explosive energy of this eruption. So this is a view looking south from near the island of Sabuku, which you can see on the map, the bottom right, looking south towards Krakatoa. Now, Sabuku, we can see that the vegetation was extremely damaged. There's burnt vegetation over all the island. So the forest has been destroyed by the event. And near the base of the island, you can see a trim line, which marks where the tsunami inundated the island and scoured vegetation. So there's a very clear mark there that shows the height of the tsunami. Now, Sabesi, which is nearer to Krakatau, was almost entirely stripped of its vegetation, being that much nearer the source, and had a higher trim line. And you can also see floating on the sea surface these rafts of pumice, the products of that explosive eruption. So just to highlight those characteristics there. So this was a very intense explosive eruption. It formed pumice-rich ignimbrites, the products of pyroclastic density currents. Those ignimbrites certainly entered the seawater. We know that because the deposits of those coat the islands around Krakatau, and they also built up the seafloor north of Krakatau, forming sort of temporary reefs and islands composed of this pumice deposit. So there was thick ignimbrite deposits, tens of meters in thickness in places, dispersed around the vent site. So there was definitely a very large volume of pyroclastic material entering the surrounding seawater. You can also learn something by looking at the form of the islands before and afterwards. So this is the last map of Krakatoa that was made before the culminating event. So as I said earlier, the eruption had started in May, so there was interest in what was taking place, and surveys of the island. So this survey in August the 7th highlighted that there were many active vents shown in red, and you can see those vents are aligned broadly north-northwest. That alignment is where the deeper part of the caldera failed. It's also the alignment on which Anak Krakatau became active, around the site of D on that map. So the same vent system appears to still be being used by Anak Krakatau. So that was in August 1883, and then after August 27th, 1883, you can see the portion of the island that had disappeared in the eruption, and you can see the seawater depths in red, showing the caldera subsidence in that area, depths of 250 meters or so in places. What you can also see is that the two islands to the north have been extended. They've grown because of these thick ignimbrite deposits. So they've actually become larger because of all the material evacuated by the eruption. So just to point out those two features. And finally, the other piece of information we have to sort of understand this event is there is a tide gauge record of the tsunami wave itself. Now, this is a record from August 26th to August 27th. So it's a whole day period, or slightly more than a day, in fact. And just to point out again, there are many small tsunami waves detected on this record. So all these ones were before the 10 a.m. tsunami. These were the smaller tsunamis that were damaging in the Sunda Straits, and likely PDC generated, so from smaller PDCs earlier in the eruption. But you can see the magnitude of the 10 a.m. tsunami was much, much larger, really extreme in terms of the relative scale to the earlier events. So several small tsunamis earlier, but something in particular generating this very large scale event at 10. So we still, as I say, don't have an excellent understanding of the precise mechanisms that generated these particular tsunamis, and this is something we would like to improve our understanding of. So it's quite likely that these smaller tsunamis have because they occur many times during what we know was an ongoing eruption, it's quite likely they were PDC generated, although we can't necessarily be sure of that. Now, there are, you can put forward different options for the 10 a.m. event. Could it simply have been a larger version of those PDCs? Well, perhaps that's possible. But I think that needs to be addressed in terms of whether there was sufficient volume of material in that 10 a.m. phase that could really be responsible for generating such a large wave. We know that the eruption had been going on for many hours prior to 10 a.m. And these PDCs that generated the earlier tsunamis must still have been fairly substantial events in order to generate those waves. So whether there is enough volume that could really be emplaced in that single 10 a.m. episode, I think is still a question that needs addressing. If it's not just PDC generated, then could there have been other processes that combined to form that tsunami source and make this event stand out? Well, I think the two main options are, what we know is that at some point the caldera collapse occurred, the main phase of that caldera collapse. We know that because the island is no longer there. We know that from the dramatic subsidence that occurred, forming this 250 meter deep basin. And the high sides of Rakata Island from the main peak that exists today were created in this event as well. So there may well, accompanying that collapse, have been some form of breakup of the volcanic island and landslide type processes as well. So perhaps this combination of processes during the culminating main explosive phase of the eruption could have formed a rather more complex tsunami source, which makes this event stand out. So I think this is a question that still needs to be addressed further, and this is something that we're aiming to do by looking again at this event to better understand the sequence of the eruption, the volumes involved, and to then apply models to test whether a PDC mechanism, for example, alone could be responsible for these very different tsunami magnitudes. And this is work that is sort of ongoing, but which we started really through fieldwork in 2019. You can just see some pictures here of the various people involved, including from ITB, in this work. So we have some drone images of the ignimbrite deposits at Krakatau that you can see here in the center. And what is clear from these ignimbrites is that these are complex deposits. They're not consistent with being the product of a single very rapid catastrophic event at 10 a.m. say. These deposits are built up over many phases of PDC generation. You can see that from the internal structure of these. There are several more massive units. There are some finer bedded units. But we can see this very lithic rich unit that comes in quite high up, quite late in the event, and which is likely to mark the main stage of the onset of caldera collapse. So we would like to work further on these to sort of start to reconstruct in finer detail the processes involved in this eruption. So I'll now move on for the last part of the talk to 135 years later, the construction of Anak Krakatau, which has been built up, as I said, along that alignment that was active in 1883. And this is a satellite image of Anak Krakatau before it collapsed in December 2018. This map was constructed in the 1990s from bathymetric data, but I think it shows quite clearly for you the setting of Anak Krakatau. So you can see Rakata here, which is the remnant of the former island of Krakatau, and this is the area where I say perhaps there was failure of this island accompanying caldera collapse. You can see that this forms a high peak. Now the active vent alignment is in the center, this sort of scarp on which Anak Krakatau is constructed. And you can see that Anak is perched on the edge of that, on a fairly steep slope, and was building up. And it failed into that basin to the southwest, so into the blue area on that less stable side. So, as I've said, Anak Krakatau emerged above sea level in the 1920s. And this is actually quite important for understanding the stability of the volcano. So as I've already shown, it was perched on this scarp. So it had a gentle slope on one side and a steeper slope on the other side, and the vent came up on that edge of the scarp. And the island from its early period had quite asymmetrical growth, with deposits on the gentle slope building upwards, but deposits not being able to build upwards on the steeper side. So we'll see that from these maps. So just first of all, to really emphasize what happened in December, this is a satellite image, a SAR image from before the event. And then in December, about half of the island failed. So you can see that here from December the 24th. On December the 22nd, around half of the island, the southwest half of the island, collapsed into the sea. And that encompassed all of the younger cone on Anak Krakatau, the sort of the younger parts of the deposits. So that links, as I say, to the importance of understanding the growth history of Anak. So I'll just talk through that growth history here. The red line is the alignment of those 1883 vents. The blue contours are Anak Krakatau before it failed in 2018. And you can see the steeper flank on the southwest side from those black contours. So in 1935, the island already had this asymmetrical form. This was the submarine phase of activity. So Circean style eruptions, forming fine ash deposits and building up a tough cone, which is likely to be quite well indurated. And this cone, these deposits build up on the northeast side, on the gentle slope, but on the southwest side, you can already get a sense that these are perhaps failing slightly or more mobile, and not building up as rapidly on the steeper southwest side. Now we can actually see evidence for that retreat between 1935 and 1936. So you can see part of that island has eroded away, maybe through a series of small slope failures, maybe through other erosive processes, but really developing this asymmetrical form. Continues to build up through to 1950. 1952 actually looks very similar to how it looks today. And then 1960, finally, the magma has stopped having access to seawater. The crater region, the vent has become enclosed. So we move from phreatomagmatic Circean activity to normal subaerial volcanism. And this again is quite an important shift in behavior, because without the seawater interaction, there's no longer explosive, highly fragmentary volcanism. And so the magma is now coming out as lava flows. These are the first lavas. And the lavas cannot flow onto the flat northeast side. The lavas will go down slope, and they're building up on the steeper slope side. So the lava deltas are building up on the southwest. So they're giving the island quite a different form to its previous growth history. And we can see that continues, and this subaerial activity also built a pyroclastic cone. So we have this sort of loading on the southwest side that previously was not particularly underlain by the tough cone stage of Anak. So just to piece all that together, we can see how the island grew through time, first of all on the northeast side, and then growing outwards on the southwest side once we had that subaerial stage of activity. And I've just sort of plotted up that sequence of evolution here of Anak Krakatau on this graph. So we can see northeast of the scarp, rapid build up through to 1960. And then after 1960, actually more extension of the island on the southwest side, the side that failed. So we're loading the island after 1960 on the steeper sided flank. And so we can then sort of draw a cross section through the island of this type of structure, the asymmetrical blue stage up until 1960, and then building out lava deltas onto the less stable side. So the collapse, when it actually occurred in 2018, obviously there's an important question of, was there a particular process that triggered this event or that led to the failure? Or is it not possible to identify such a process? And was this just the consequence of long-term growth and gradual gravitational instability? And this is still a question that is difficult to answer. There is some evidence of deformation of the edifice occurring over a gradual period, but it's hard to know how anomalous that was. We have been looking at the magma that was erupted across the event before and afterwards to see if there's evidence of a change in the nature of the magma system, maybe fresh magma entering the system that could have triggered the event. And at present, it's not clear that there was a particularly substantial shift in behavior, and the very intense eruptive activity that took place after the collapse, in many respects at least, appears to have been a consequence of the collapse. So triggered by the failure, but there do remain some uncertainties in that. So at the maps at the top, you can see the change in the morphology of the island. After the collapse on the 23rd of December, there was very vigorous phreatomagmatic activity again. So once again, the magma interacted with seawater. There was ash generated through highly fragmentary explosive processes, and this rapidly built up the island again. So it buried much of the collapse scar. And actually, even within about 2 weeks, the island had dramatically changed and looked very similar actually to how it looked in 1952. So I'll show those two maps there. You can see a picture of those intense eruptions, and one of the things we've been working on is sampling the stratigraphy of that activity and then looking at the products of those events through the eruptive periods to try to determine where the magma was coming from in the system. Were there any geochemical changes, evidence of fresh magma input, changes in magma ascent rate, and so on through this event. And as I say, at the moment, the results suggest that decompression of the system following the failure resulted in this very intensive explosive activity. But it's less clear that there was necessarily fresh magma input in the lead up to the event, although there are still some aspects of the results that we need to interpret in that regard. The other work that has been done is to look offshore at the deposits from this event. So just as I showed at Ritter, we can look at the outcome of an event to better understand what took place, to reconstruct the event itself. And you can see here at the bottom right, these landslide deposits, very, very large blocks. So unlike Ritter Island, the failed mass doesn't appear to have disintegrated to a very large degree. It traveled maybe 1.5 kilometers beneath the seawater, but has quite a sharp front. Now, that's maybe not what would necessarily have been expected from this pyroclastic cone, but maybe parts of the lower edifice of Anak Krakatau were better lithified and stronger. Regardless of the style in which it fragmented, this was clearly capable of still failing rapidly enough to generate a very damaging tsunami. So the style of breakup is not necessarily of sort of primary significance in that. This was still a fast-moving, rapid landslide failure. We can use this seafloor mapping. So I just show one profile through here to sort of reconstruct the event volume. This suggests a deposit volume of around 0.2 to 0.3 cubic kilometers, and a primary failure volume of a similar order, and that fits with what we've reconstructed severely. So about 0.2 cubic kilometers of rock failing from the volcano. We can see a few other features on this map. You can see evidence of the burial of those deposits from that very vigorous subsequent activity, and this has sort of obscured a lot of the evidence of the collapse. And this type of process means that the older volcanoes, it may not be very difficult for us to see evidence of such events because they very rapidly can become obscured. So we've also used this reconstruction of the landslide to test our understanding of tsunami generation and to test current tsunami models. So we can reconstruct the event as we think it occurred and then use that within numerical tsunami models to check if those models are accurate and can reproduce the observed tsunami. And what we find with these is that a 0.2 cubic kilometer failure does reproduce many of the characteristics of the tsunamis precisely. So that's both the amplitude, the height of the waves, and the pattern of wave generation. So I'll just show one output of one of these models. This is work done by collaborators at the University of Rhode Island. And we can see the leading wave here. This is 5 minutes after the generation of the tsunami, or 5 minutes or so. And And you can see that the wave height in the open water here of the leading wave is about 10 meters. We know that the leading wave, when it impacted these islands very near Krakatau, like Rakata, the run-up heights were up to about 80 meters. So it's very extreme height of the wave. And then this dissipated gradually as the wave energy spread through the Sunda Straits. It's quite a complex pattern of wave propagation because of the bathymetry and the various islands that the wave is interacting with. But we can see the elevation here at about 30 minutes. So 30 minutes was about the time it took this wave to reach the shorelines of Java. Quite a short time scale. And the model output matches very well the measured wave. So we've concluded from this that a 0.2 cubic kilometer landslide is a reasonable approximation of the size, but also that there's no need to invoke other mechanisms to generate this tsunami. So we think it was purely landslide generated rather than, say, explosive activity. Okay, so this is my final slide, and I just want to sort of finish with a few conclusions. So I hope this has emphasized that volcanic tsunamis remain one of the most challenging volcanic hazards to forecast and mitigate, and there are many things we still don't understand well about these events. This means that historical events such as Anak Krakatau, Krakatau 1883, Ritter, these events of things that have occurred and that we can learn from are important to better understand these hazards. New observations of 1883 we would like to use to test the mechanism of tsunami generation for these different types of tsunami that occurred during the event. And Anak Krakatau and Ritter are important historical events for advancing our knowledge of landslide, of lateral collapse generated tsunamis, and important also to test and develop tsunami models, as well as our understanding of the precursors to these events and their impacts. Okay, so I'll stop the share there and hand over to Mirzam.
Okay, thank you very much, Chef. Very nice presentation. So now we are in the question and answer session. Maybe you can see on the Q&A, there are already 3 questions. The first question is still in Bahasa. I will translate for you. from Hardiana Mutmainah. The first question is how long the tsunami will reach the beach or the beach line? Start from beginning of the eruption.
So the travel time of a tsunami is dependent on a few parameters, but the most important parameter really is the water depth, because that determines the velocity of the tsunami. So this is a very important consideration, really, to think about timescales over which, say, between the initiation of an event and the amount of time to communicate or provide warning and so on. Yes. So at nearby coastlines, so if we look at Krakatau and Java, that timescale was 30 minutes. So it was about a 30-minute travel time before the leading wave reached the shoreline of Java, which is a very short window, really. Now, and that would have been similar in the 1883 tsunami at Krakatau, and indeed at Ritter for those nearby islands. We're talking, places within a few kilometers.
Yeah.
I mean, the coastline of Java is 50 kilometers away, but it's quite shallow water. But that's a 30-minute time, so not a very long interval for the areas impacted by the highest waves, and islands nearer, you're talking a few minutes,
right.
So a short time.
Okay, so depend on the some parameter, right? Okay, and then the second one is so which one will produce big tsunami, earthquake in the submarine or due to the eruption of the volcano?
Yeah, so the characteristics of tsunamis generated by these different mechanisms are quite important for their propagation behavior. So, and particularly the wavelength of the generated tsunami. So an earthquake mechanism, because you've got deformation of the seafloor over a substantial area, so the fault rupture in an earthquake may have a width of 100 kilometers or so, say, and the deforming seafloor, an uplift of maybe on the order of 10 meters or that sort of scale. So this is a large area that's being displaced, and this generates a large wavelength tsunami. So the tsunamis, say, generated by a large subduction zone earthquake, because of their long wavelength, they can travel without losing energy over very large distances. So the maximum wave height may not be as extreme as these volcanic examples. It may be on the order of, say, 10 meters, but that could propagate over very large distances without losing a lot of its energy. In volcanic events, we tend to be displacing over a much smaller area, generating potentially very extreme amplitudes, but the wavelengths are shorter and the energy dissipates as that wave spreads from that smaller area. So you see more rapid decay. So this is why, like the Anak Krakatau tsunami, we think near the source, the waves were maybe 50 meters. But by the time they reached the coastline of Java, they were a few meters. So you had rapid spreading of that energy. And so the magnitude can be very high near the source, but they will not spread as efficiently over a very large area.
I see. Yeah. Okay. And then the last question from here, Diana, is how we know there is the one area is affected by the tsunami? Is there any specific identification from the product?
So do you mean for reconstructing an event in the past?
No, I mean to identify this is a product coming from tsunami, or this is a product from sedimentation or from direct from volcanic eruption.
Yeah, okay. So this, I mean, I think this is not an area that I have so much experience in, I must say, but I think it is actually very difficult to reconstruct the past impacts of a tsunami and identify the deposits of a tsunami in some cases versus other events. Now, in certain settings, it can be clear. So if that tsunami has carried in, say, beach material, shells and marine sediment into a stable environment, such as a lake, then there will be a very sort of clear deposit from that is of an anomalous sediment type. And there are examples of that. I mean, there's an example in the UK, actually, that's quite well known from a submarine landslide off the Norwegian margin about 8,000 years ago. And this forms a very clear shell-rich layer, and we can reconstruct the height of the wave and so on from that. But in many environments, I think tsunamis do not leave a clear mark in that way. And I think it's quite difficult, therefore, to reconstruct even the occurrence of a tsunami, but particularly more specific information like the inundation distance or the height.
Okay, thank you, sir. And then now we are going to the second question. Maybe you can check to the Q&A from my student, Muhammad Ilham Fatoni. Okay. Can you see the question, sir?
No.
There are some different mechanisms that could trigger tsunami caused by volcanic activity. Are there any specific characteristic of the tsunami wave that can be distinguished by its mechanism?
Yeah, that's a good question. In theory, I suppose there are, particularly the wavelength and the sort of frequency characteristics of the tsunami will depend on the style by which the displacement is occurring, the duration of that, and the area of that disturbance. But I think in reality, it would still be very difficult to discriminate, say, between a landslide source and a pyroclastic density current source without very precise knowledge of those source options. And in reality, in most volcanic events, we don't have that precise knowledge until after the event, and then we're seeking to reconstruct it. So I think that's difficult, particularly with sort of mass flow displacement type sources. Maybe with explosion generated sources, that these would have quite distinct characteristics because it's a different mechanism. But anything that is volcanic material, whether it's hot or cold, landslide or PDC, I think the characteristics are broadly similar, really. And without knowing quite specific details about the eruption source, it will be hard to distinguish that.
Okay, Seb, thank you. Before we continue to the next question, is there any question from the panelists? Pak Hendra, maybe do you have any question?
Yes.
Yes, please.
I thank you for the opportunity. So I agree with the complexity of the Krakatau Island, especially from the point of view from the regional structure around in the Sunda Strait. So what do you think about involving of the trend of regional structure? And the second thing is, if we look the morphology, the before 1883, so you see the direction is more northeast, southwest. For the if I'm right, what do you think? So in our seismic data from the hypocenter, from the data in 2016, we have some delineation for the hypocenter point in the direction of west to southeast. So what do you think from the point of view from you? Thank you.
Yeah, I think that's again a very interesting question. That there are regional tectonic controls really on the volcanism at Krakatau, and that could be both in terms of the magma ascent routes feeding right through to the structure of the volcano as a whole and its stability, and also influencing the caldera subsidence. And I think all of those show an influence of regional tectonic fault patterns. So the vent alignment from 1883 before the catastrophic eruption shows a very strong north-northwest, south-southeast alignment, which matches broadly with sort of an alignment of volcanic structures that stretches right across the Sunda Straits, I think, from the southeasternmost part of Java up towards Sumatra. So there appears to be, and in some ways, Krakatau is in quite an unusual tectonic setting. It's between these two much larger islands in an area perhaps that is an inflection in the subduction zone structure, possibly subject therefore to some extension or rotation.
Yeah.
And you could question, well, does this mean that the flux of magma at Krakatau is unusually elevated because of this? Maybe even the extent of melting, I don't know. So we have perhaps a particularly sort of active volcanic system in this setting. And then the structure of that system as a whole does appear to show an orientation that reflects these regional patterns. So I'd agree that the vent structure before 1883 shows that the scarp of the caldera wall, the caldera actually is a bit more complex than some reconstructions sort of suggest, but the main part of subsidence appears to have been to the southwest. There was also some subsidence to the north east. That's evident from the maps before and afterwards. But again, this vent alignment appears to have really controlled the caldera subsidence. And you could argue, well, does that even reflect where the magma beneath was stored from and erupted from? So is that also being influenced by the sort of the magma storage geometry being influenced by this faulting. And then the pathway of Anak exploited the same route, was built up on the same scarp, a fault scarp, really. And so, I think there is this overriding influence of the structure on which Anak was built that's gone right through to controlling the stability of that edifice, and potentially the sort of longer term deformation of that edifice as far as we understand it. So yeah, I mean, overall, I think it's an important factor.
Yeah.
The direction of failure, I don't think was random, but was influenced by this underlying structure.
Thank you.
Yeah. Okay, Pak Hendra, thank you.
Yeah.
Yeah, so because we know that there is the changing of the subduction style from oblique in Sumatra become perpendicular in Java. So that's why we have something like tearing, northeast southwest trend. So that's why the opening of the Anak Krakatau, Sebesi, Sebuku tend to the southwest. Yeah. Okay, Pak Hendra, thank you. And now we are going to the next question from the anonymous attendee. Do volcanoes related to the marine system, for example, volcanic island, pose the hazard of tsunami generation?
So, sorry, could you repeat? Volcanoes in which system?
Yeah, do volcanoes related to the marine system, for example, volcanic island, pose the hazard of the tsunami generation?
Yeah, okay, yeah. So I would say, from what we know, volcanic islands in all tectonic settings, so this is intraplate settings and arc settings, and even entirely submarine volcanoes, we know from mapping around these that they are capable of failing. Those structures can be unstable in any of these tectonic settings, and they can undergo large-scale, likely rapid landsliding. So I think this can occur in any setting. But as I emphasized right at the start of the talk, these are infrequent. There are very few such events in the historical record. And there has been some focus at places like the Canary Islands, for example, on these really, really big landslides, which no doubt could have very dramatic consequences, no matter how the landslide sort of fails. These are extreme volumes. But those are also very, very infrequent, even in a global context. Maybe events that occur once every, on the order of tens of thousands of years. There are many more small islands in subduction zone settings. And although the landslides they generate are correspondingly smaller, we can see from events like Anak, Krakatau, and Ritter, the landslide doesn't need to be enormous to have very devastating effects. So, and these smaller islands are also likely to be the source of sort of more frequent events in a global sense. So we have events such as Anak, Ritter, Unzen, and one or two others in the historical record. But it is still globally sort of, these are not common in the context of volcanic hazards.
Okay, thank you, Seth. And then the next question from my student: how to make a tsunami prediction modeling? Should we apply the same way for the tsunami? Triggering by the earthquake, or different way? Yeah,
I think. This remains the big challenge. I'd absolutely agree. How do we move from learning about something after the event has happened to really looking at a scenario before the event, a scenario that we can demonstrate is precise and realistic, and identify when the precursors to that scenario might be evident and could then be mitigated. And this is a very difficult thing to address, and I think our current approaches and knowledge do not mean we're not in that position yet. to model scenarios, I think we can learn. First of all, we need to learn from events like Anak Krakatau. If we can demonstrate that we understand those events well enough to be able to accurately model them numerically, which I think we can already show. I mean, the models they're still a simplification of the landslide process, but they can reproduce the overall characteristics. So that's an important first step. But then the next is to recognize at specific volcanoes, what's the potential for instability? What is a possible event that could happen? How would we recognize if that incipient failure, so the build-up to the failure was occurring? And then tsunami models are valuable, of course, in understanding what the impact of such an event could be. But yes, the recognizing when an event like this would occur is still very difficult.
Okay, Chef, thank you. Before we continue with the remaining question from the attendee, I would like to say hi to my colleague, Professor Amy, Dr. Aswan, Dr. Rina, Dr. Andri. Maybe do you have any question to Sebastian? Maybe Aswan, you just come back from the Sunda Strait. There is something new.
Hello, Sebastian.
Hi.
Thank you for nice presentations. Once we met in our department last year, probably.
Yeah.
I just need your confirmation since my focus is about also tsunami deposits. May I see once more your slide that show outcrops in Panjang?
Yeah, of course. Yeah. Yes, so there is a tsunami deposit preserved at the base of the tephra fallout deposits. Sorry, this will take a little while for it to... I think it's still loading. Yes, so there's on Panjang, this was maybe 100 meters or so inland, but still quite low lying. And interestingly, on the eastern side of Panjang, so sort of sheltered from the main direction of the tsunami. And at the base of the ash deposits there, between the soil, which has roots in, and the ash deposits, there's a prominent white volcaniclastic deposit, which also included a small amount of shell material, of marine shell material, which we've inferred was a tsunami deposit. And it shows that, here we are, it shows that the
this one, yeah.
The ash deposits.
So above the soil, is it 2018 tsunami deposit above?
That's right. 2018 tsunami deposit. Yeah.
So the white one, is it content of pumice or beach deposit?
It's mainly pumice, rounded pumice from 1883, remobilized from the beach. There's a small amount of shell bioclasts in there as well, but it's mainly pumice.
How far the location from the beach?
About, I can give you the exact locations if you'd like afterwards. But it's about 100 meters, no, maybe 200 meters. But probably it's very low lying, so an elevation maybe of 10 meters.
So after the pumice, it's there is a 25 centimeter well bedded ash.
That's right.
Also from 2018.
Exactly. From the ashes from the Surtsey and phreatomagmatic explosive activity that occurred after the collapse.
And so how about the above the ash bedded, the white one? Is it a beach deposit? Or
it's just reworked ash because we're near the coastline here, and there was a lot of remobilization by rainfall of the 2018 ash. So the top part is not primary, it's just remobilized ash, and it's just dried out at the top, which is why it's pale. But I have samples of this and can give you full information about them if that's useful.
Okay, thank you. Because when we are in the field, but just on not in Panjang, is along the Kalianda beach, we cannot find the thick, well-bedded ice like in your picture. But the tsunami, we find tsunami, but the tsunami deposit, but it's just content of the beach deposit and some pumice also, but not dominant the pumice. Yeah, but it's just along the Kalianda, not in Panjang. So what do you think? How about the S is logically? Is it cover the whole area around Sunda Strait, or just locally in Panjang? Maybe there is some specific topographic control there.
Yeah, just locally. So if we look back at this picture here, I mean, Panjang is only maybe 3 kilometers away from the vent, so you can see the plume here. The ash-rich plume was directed to the east, and you can actually see the ash falling out over Panjang here. So that's Panjang Island there. So there were thick ash deposits on Panjang, but I think by the time the plume reached the Java coast, the deposits were extremely thin. I think Mirzam has sampled them and observed them. So much thinner than in Panjang. If I just go to the final picture, this is also of Panjang here. So this is a picture of Panjang. You can see the vegetation damage from the ash fall. So there were maybe 30 centimeters or so of ash deposited on Panjang, but only because this is very near Anak, Krakatau, and directly in the path of the plume.
Okay, maybe it's because the directly the ash go to the Panjang area.
That's right.
When I saw your picture, is look like there is two island, maybe Subuko and Subesi, that protect the area of the around Kalianda. So probably that's why, because that's two factors, not directly to Kalianda, and also maybe there is from Anak Krakatau, there is some island before before the wave go through the Kalianda beach. Probably, so maybe it's because it's due to that factor. The sediment, the tsunami deposit is not too. Maybe the tsunami deposit is almost the same thick, but there are no bedded ice there, as we observe there.
Yeah.
Okay. Thank you for your explanation.
No, thank you. Yeah.
Thank you, Pak Aswan. So if I'm not mistaken, we also found some outcrop in Sebesi or Sebuku in the first split campaign, or on the second when you went there with Edo, maybe.
Yes, on Sebesi, certainly the tsunami damage was very evident. We didn't particularly find deposits from the tsunami as such, but on southern Sebesi, the damage was at least to a height of 10 meters inland on the south side. But I mean, this goes back to the other question about the evidence of past tsunamis. There was no real clear deposits on Sebesi. So that in the longer term, there would be no sort of geological record. I think on Panjang, because of the burial of the deposit by the ash, it's well preserved, the tsunami deposit. In terms of ashfall, I'm not aware of any direct ashfall reaching Sebesi. I mean, there may have been very small quantities, but it really was most intense on Panjang and reached Java, as you know, but was very fine and thin, the deposit there.
Okay, Chef. So we still have some question from the audience. Is it okay for you?
Yeah, of course. Yeah.
Okay. The next question from Rudy. So do you know which is the biggest volcanogenic tsunami in the world during the human history? Is it from Krakatau?
Well, it depends on how well recorded it is, I suppose. I think in the recent historical record, the highest magnitude wave would be from 1883 at Krakatau. That's not the most extreme wave that's been measured, I suppose. There was quite a small landslide in a global context in Alaska in 1952 in an enclosed bay that displaced the wave on the opposite side up to, I think, around 500 meters. But this was sort of literally the water was pushed up from one side of the fjord up to the other side. But of volcanic events, yes, Krakatau would be the largest historical event. But there is evidence from older geological reconstructions of bigger waves. So in the Cape Verde Islands would probably be one of the best examples. The island of Fogo in the Cape Verdes, which is in the Atlantic Ocean, had a very large scale lateral collapse. The age of it escapes me for now. It's several tens of thousands of years old. And on another island in the Cape Verde group, there are marine rocks or rocks from the coastal stratigraphy, which are preserved very high up, I think a couple of 100 meters above sea level. And so they're out of stratigraphic sequence. These rocks have been carried higher up. And so the only real explanation for how they could have got there is from an extreme wave. And so these have been attributed to a very large scale tsunami from the Fogo collapse. So there is evidence of sort of even bigger wave amplitudes and things like that.
Yeah. Okay, Chef. And then the next from my student, this is related to the floating material, pumice rough, that can be deposited as layer in the surrounding island or the land on the coastline. Can we identify that this pumice deposition coming in one episode or from multiple episodes maybe?
Yeah, it's a good question about the pumice rafts. I don't know, to be honest, how much information you could reconstruct from a past deposit of these in terms of sort of the sequence of a process. I mean, the pumice rafts from 1883 are reported to have been transported right across to the African coastline, for example. So they floated for many months. And this has been observed in other submarine eruptions as well, that pumice rafts can last for many weeks or even months and be dispersed very widely. They will ultimately become waterlogged and sink or broken up through abrasion. So I suppose in theory this means their deposits could be quite widely dispersed, but I'm not sure if it would be straightforward to reconstruct from a deposit the sort of characteristics of the source event, because their spatial distribution would also be quite erratic.
I see. Yeah. Okay. Yep. Thank you. And the last question from my student, from the 6 possibilities you mentioned before. So which is the dangerous one? Related to the collapse of the flank of the volcano, related to the pyroclastic, or
so sorry, what was the question about which one?
Which one the dangerous one from the 6 process that probably triggering the tsunamis related to the volcanic eruption?
Okay, yeah. Okay, so it's the question sort of which is the dominant process, or I think, yeah. I mean, I suppose that they're all plausible mechanisms. Is the point that's being made, but probably the most common way in which volcanic tsunamis are generated is by pyroclastic density currents entering the ocean. There are many small examples of those processes in the historical record. So during the 1995 eruption of Montserrat, during events at Stromboli in Italy, there are many examples of small tsunamis being generated by PDCs entering the ocean. But these tend to be very localized. In many cases, they've not caused significant damage. Sometimes the damage has occurred, but is over quite a limited area. So these are not, most of these are not large events. If you looked at the examples of the most damaging volcanic tsunamis, then probably the more dominant mechanism is flank collapse, just because that's a mechanism that can mobilize very large volumes of rock in a single event. But that's notwithstanding the example of Krakatoa in 1883, which I would, my interpretation is that this is most likely to be a complex source, certainly involving PDC and placement, but maybe with additional factors in that final stage of the eruption.
Okay, Chef, thank you very much. And then is there any question from the panelists? Bu Emi, maybe? Bu Rina, Pak Andre?
Yeah, may I? Hello?
Yes, Pak Andre, please.
Hello?
Yes, please.
Can you hear my voice?
Yes.
Yes.
Very clear.
Okay, thank you very much. Nice presentation, Sebastian. So I have maybe 2 or 3 questions. First, is that active tectonic system in Indonesia, maybe from 2014, from the big earthquake in Aceh, influence to also some volcanism in North Sumatra until Krakatau. It is the best question. And the second one is the landslide in 2018 is also triggered by earthquake, not only the volcanism. And the third question is the explosion in Krakatau can become a volcanic massive explosion, volcanic massive sulfide extreme? Is it early state of volcanic massive sulfide state? So, thank you.
Okay, thank you. I mean, your first 2 questions, I suppose, are really about understanding if there are relationships between between seismic activity and volcanism. And I mean, I think there are probably sort of interconnections between these processes that we still don't well understand. There are some good historical examples of triggered eruptions, or what appear at least to be triggered eruptions, where there's a volcanic eruption that very shortly follows a regional earthquake, and where the passage of seismic waves through the magma system has maybe altered the stress, perhaps caused nucleation of gas phases, for example, or some other process that has disrupted the magma system and then led to the onset of an eruption. So there are examples of that occurring, and I think that it's easier to link those processes when the time scale is very short, because there's a better argument, if you like, to make the direct link. I think it's much more difficult to say, was this system affected on a timescale of a few years by a large regional earthquake? I think it's difficult to say categorically either way that no, the Aceh earthquake, say, had no influence on activity of the Krakatau system, or the converse. But given that we have examples of events that are triggered on a short time scale, it does seem plausible that there may be longer time scale disturbances of magmatic systems, which ultimately propagate in the form of an eruption, but maybe with a longer time lag. So I mean, I'm not aware from anything that I've sort of read or worked on of sort of direct volcanic impacts of the Aceh earthquake, but that's not to say they're not there. In terms of Krakatau specifically, the precise trigger of the 2018 collapse, I think, is still, from the data I'm aware of anyway, something that we don't fully understand. It's clear that this volcano was building up on a relatively unstable position in terms of the scarp it was built upon. There is evidence from the INSAR satellite observations and some other observations that there appears to have been perhaps a longer term gradual deformation on a sort of relatively subtle scale. Exactly what caused on December the 22nd that mass to fail is the more difficult thing to pinpoint, I think. Was this just the consequence of a long-term gradual gravitational deformation? Is there a particular event that pushed the system over the edge? I think is still unclear. We know that the eruption in 2018 was quite vigorous, but it had started in June and had been very intense in August and September, but the failure didn't happen until December. On the day of the failure, there was some quite intense explosive activity, but not activity that stands out relative to what happened in August, particularly. So it's not clear to me from those observations that there was something particularly unusual in the volcanism that day, at least from what we were able to currently reconstruct. Whether I know there are some seismic signals from the time of the event, but I think some of those have been attributed to the failure itself, so a surface signal generated by the collapse. Whether there's also a sort of earthquake type signal, I'm not sure. That's not something I'm familiar with from the data I've seen, at least. But it'd be very interesting if you have other perspectives on an earthquake type trigger.
Okay, Sebastian, Pak Andri, hopefully Sebastian already answered your question because the time is almost up. Some attendee and my colleague are interested with all reference from Anak Krakatau. Is it possible if you share the PPT, Seb? And also the reference
feel free. I've sent it to you, haven't I? So if you'd like to share it with, that's fine. That's okay. Yeah.
And also
Thank you, Dr. Sebastian.
They're interested with the old reference on Anak Krakatau that we already collect maybe from Leiden University and many sources.
Yes. Yeah.
Okay. Okay, ladies and gentlemen, I think we have finished the guest lecture of the day. We have learned a lot today regarding to the tsunami hazard at island volcano. May what we have learned today will be useful for us in the future. Before we close this session, let me to inform you that 2 weeks later, we will have another interesting guest lecture from University of Tasmania. The topic is related to the volcano and economic mineral. Please check the date through the official Instagram of our faculty ITB. And then, okay, before we close, would you please to open the camera for the panelists? We will take a picture together. Dr. Idam, would you please have to take the picture?
Yes, sure. Okay. Okay, please open the video. Yes. Pak Aswan, Ibu Emi. Okay, let's take picture. 1, 2, 3. Okay, once more. Wait. Okay, once more. 1, 2, 3. Okay, thank you very much.
Thank you, Idam.
Thank you.
Thank you, Dr. Sebastian. Thank you, Pak Aswan, Pak Hendra, Bu Emi, and other panelists, and also all the.
Terima kasih.
See you next week and have a nice weekend.
Thank you for the invitation, and thanks everyone for all the questions as well.
Yeah. Thank you, Seb. Yeah.
Thanks. Okay. Bye.
Bye. Terima kasih Pak Hendra, Pak Aswan,
Sama-sama, Pak Hendra.
Saya live ya, izin live
Ya,
ya.
izin live ya.
Oke, makasih Bu Emi. Oke, Chef, I will talk to you later. Ya.
Yeah, right. Thanks, Mirzam.
Yeah.
Thanks very much. No, it was good. I enjoyed that, and I hope it was informative and good discussion. So yeah, okay. We'll be in touch soon as well. And yeah, if anyone has questions, feel free to forward them. Or like Aswan was asking about the tsunami deposits. Maybe if he wants more information, we can discuss it, and I can give him details.
Okay. Thank you.
Okay.
Yeah.
All right. Thanks.
Yeah.
See you soon.
Yeah, see you soon. Bye. Pak Idan, terima kasih. Bu Dina, terima kasih ya.
Ya.
Ini Q&A-nya dicatat aja, kita kirimkan kali yang belum semua ya. Akan ada beberapa yang nanya juga di chat ternyata.
Ya, kalau itu sudah saya save, Mas. Tinggal ini sebentar. Q&A saya mau ini juga.
Yang di chat udah dicatat kan?
Sudah saya save ya. Tadi udah ada masukan dari Pak. Bentar, untuk ininya saya save dulu.
Itu saya pikir yang Rite Island itu lebih mirip sama Banda Api itu daripada mirip sama Krakatau itu.
Iya, Mas.
Yang di Papua Nugini itu. Nah, ini harus ke sana nanti kalau ke Ambon. Harus ngajar ke sana terus punya murid di sana tuh. Di Banda Api.
Saya copy paste aja kayaknya ya.
Sudah bisa.
Sebentar.